evening, everyone. First of all, I would like to thank you, our lecturer, and all my friends for giving me this opportunity to present our project today. Today, I will be presenting our project titled Kinetic and Derivation in Solid State Fermentation. This project focuses on the application of calculus, especially derivative, in agro-product technology and fermentation process. Our project is designed as an interactive bioscience learning platform. The main purpose of this project is to help students understand how fungal biomass change during fermentation over time. Instead of learning only those theory use can interact directly with the simulator and observe how the graphs and growth patterns change instantly. In this project, we use Xyropus oligoropus as our main example because it is a commonly used in tempeh fermentation. We apply logistic growth model to present fungal growth during fermentation process. Besides that, we also use derivatives to calculate the growth rate. The derivative is very important because it's helpful use determine how fast the fungus grows at the certain time. During rapid growth, heat is pursued, and if the temperature becomes too higher, it can affect quality of the fermentation process. By using mathematical models, agro-process engineers can monitor and control fermentation more effectively. Another important feature of the project is the interactive simulator. User can change parameters such as the carrying capacity, growth rate, and initial inoculum size. After changing the values, the graph update automatically. The system also display biomass growth curve, determined curve, target line equation, and process state advisory message. This makes learning process more visual, interactive, and easier to understand. Our project is also related to the Malaysia agro industry, especially in tempeh production. Traditionally, fermentation depends a lot of human observation and experience. However, model industries now use mathematical models and automated systems to improve product quality, reduce spoilage. For example, when the system detects the minimized growth rate, industry will know the production is at highest point. At the stage, cooling and aeration system can be accurate to maintain a safe temperature during fermentation. In conclusion, this project shows that calculus is not only mathematically concept learned in class, but it also an important tool used in real industrial application. By combining biology, fermentation technology, and derivatives, this project helps students understand agro product process in a more interesting and interactive way. Thank you for listening, and that's all for me now.
Assalamualaikum and hi Dr. Yunani and my dearest groupmates. My name is Sajidah binti Yunani. My metric number is F2581734. So today I will present my part of our interactive website called Biocult, which is designed for sustainable food security in Malaysia. The purpose of Biocult shows how mathematical derivatives can solve real-world agriculture problems. It connects calculus with farming decisions, helping farmers reduce waste, save costs, and increase food production. This is the chosen bioscience problem. The dashboard covers 3 cases, which is MR219 paddy growth curve, red tilapia weight gain model, and palm oil content accumulation. For today, I will focus on the MR219 paddy growth curve. Why it matters? Paddy plants need nitrogen fertilizer, but farmers often don't know the best day to apply it. By using growth models, we can identify the exact timing for fertilizer application, ensuring maximum yield and efficiency. For mathematical modeling, Biocult uses 2 functions. which is first is logistic growth model, calculates plant height over time, like if, and the second one is derivative function that shows the daily growth rate at any given day. For interactive features, the website includes a live calculus calculator with a slider. So, at 55 days after transplanting, the derivative reached its peak growth rate. The interactive graph highlights this point, showing farmers that this is the perfect time for nitrogen top dressing. In simple terms, at day 55, the plant is growing faster. So, applying fertilizer then ensures better grain yield, reduce waste, and also supports sustainable farming. So, lastly, my improvement suggestion on how to make the website better is to add a download PDF button. This would allow farmers and students to export the graph and farming advice into a printable report for use in the field. In conclusion, BioCalc demonstrates how mathematics can directly support Malaysia's food security. By combining calculus with agriculture, we can help farmers make smarter, data-driven decisions. That's all from me. Thank you.
Hi and Assalamualaikum to our lecturer, Dr. Leonie and my dear roommate. My name is IZWANI Batuan Omar. My metric number is F25A2057. Today, I will be presenting the biophysical derivative simulator, an interactive educational platform that combines differential calculus and web technology to address food security issues. This project focuses on optimizing the growth kinetic of the MACD MR297 paddy variety. The core challenge is the difficulty in pinpointing the exact space of maximum biological growth acceleration, which naturally follow a logistic sigmoid curve across its 115-day life cycle. This study is crucial for helping Malaysia achieve its 100% self-sufficiency level SSL target for rice production by identifying the exact timing of the crop highest nutritional demand. Fertilizer application can be optimized to boost crop yield while minimizing chemical runoff into the environment. First, we look at the graph. Point breakdown interactive simulation. Based on the simulation, day 0 to 13 yearly growth, the biomass curve is flat with a growth rate near zero as the plant focus on establishing its root. Day 55 inflection point. T is the most critical path. The growth velocity peaked at 2.81 grams per day. This is where the plant requires maximum fertilizer top dressing. Day 16 to 19 yield formation. Total biomass continue to rise, but the growth rate slow down as energy shift from vegetative growth to rice grain production. Day 120 harvest, the plant reaches its maximum biomass of 115 grams, and the growth rate returns to zero as biological growth stops. However, I recommend updating the HTML code to include dynamic magic formulas. This the sliders, making the website much more effective and interactive for learners. That's all from me. Thank you.
A good day to our Dr. Leonie and my fellow friends. So my name is JARNITTHA and my matrix number is F25A1926. And today I would like to present my interactive bioscience dashboard, which is MD2 Pineapple, ripening kinetics, applying calculus and derivatives to predict optimal harvest window in Malaysia peat soils. So this project is developed under SFP Agro Product Technology specialization. So the main objective of this project is to demonstrate how calculus and derivatives can be applied in real agriculture and food technology situation. So this project focused on ripening process of MD2 pineapple. So in Malaysia, MD2 pineapple is highly demanded for export and food processing industries because of its sweetness and premium quality. However, one major issue faced by farmers and factories is determining the best harvesting time. If the pineapple is harvested too early, the fruit becoming sour, starchy, and low in a sugar content. So meanwhile, if harvested too late, ripening may happen. Fermentation can occur and storage quality decreases. Therefore, this project used calculus and mathematical modeling to scientifically predict the optimal harvesting stage. This bioscience problem is important because it directly affects agriculture productivity and food quality. By understanding the sugar accumulation process, a farmer can make better harvesting decisions, factories can improve product quality, food waste can be reduced, and also export quality can be improved. Besides that, this project also shows how mathematics can be applied in real bioscience and agro product technology. And here, first I will explain the graph visualization section. This graph contains two different curves. The orange graph represents the sugar accumulation level, which is function fx. This graph shows how sweet the pineapple becomes over time. At day 110, the sugar level is still low. Meanwhile, the fruit is still immature and green. At the day increase, the sugar level gradually increase, and showing that the pineapple becoming sweeter during the ripening process. And the green dot graphs represent the derivative function f by x. This graph does not represent total sweetness. Instead, it represents the rate of sugar synthesis per day of how fast the sweetness is increasing. From day 110 until around 125 here, the derivatives graphs is increased. This means the pineapple is actively synthesizing sugar and ripening rapidly. Around 25 to 30, the derivatives reach the maximum point. This indicates the most active ripening stage where sugar accumulation occurs at the fastest rate. After day 130, the derivatives quality decreases. It means the pineapple still becoming sweeter, but the ripening process is slowing down. Near 150, the derivatives approach 0, showing that the fruit is approaching over ripening. For example, the selected point 134 here. At this stage, the sugar content is approximately 12 degrees Brix, and the derivatives is still positive but decreasing. This indicates that the pineapple is already sweet enough and approaching the optimal harvest stage. And now, I'm explaining the mathematical modeling session. This equation represents the total sugar accumulation throughout the ripening process. Next, is the mathematical derivation session. It was show how calculus was applied and obtained the derivatives equation. Using differentiation and the power rule, the original equation is differentiated into the first derivative equation. The derivative equation represents the sugar synthesis rate per day. The purpose of this derivation is mathematically prove how to ripening rates change throughout the pineapple growth period. And now it's time for conclude our presentation. In conclusion, this project successfully demonstrates how calculus the derivatives can be applied in bioscience and food technology applications. By using derivative analysis, this dashboard helped predict the optimal harvesting stage based on sugar accumulation rate in MT2 pineapple. This project also proves that mathematics is not only theoretical but can also be applied to solve real-world agriculture. Learning platform can be help users better understand real industry application of calculus. Thank you.